Hello everyone. In today's lecture, we'll discuss about the AC circuit elements. Uh, we'll learn what are the AC circuit elements, their measure, and analyzing technique. So, what are the basic AC circuit elements? Resistor, resistor, inductor, and capacitor. These three are basic AC circuit elements, and their measure is impedance. We call it impedance. So. Impedance is basically represents how much current is opposed by this element while AC is applied to this element. Okay, so for example, in our DC circuit, we know about the resistor. For resistor is something resistance is something which actually opposes current through flow through this that element, and we call it resistance. Similarly, in AC circuit we call it impedance. Impedance is the measure of the opposition of current flowing through that element. uh, that is impedance, and we learn more detail about impedance in this lecture. Let's start with what is the phasor relationship for circuit elements. We need phasor relationship because in phasor relationship, or in if we discuss any circuit element in frequency domain, which is phasor representation of complex number. If we discuss any circuit element in that frequency domain, our analyzing technique or our analysis will be more easier. That means we will get a will analyze the circuit in a better way, or this may take lesser time, and the mathematical complexity will be minimized if we analyze the circuit in frequency domain rather analyzing in time domain. You will understand this variation in this lecture also. So let's start with the phasor relationship of resistor. Okay. So in resistor, we know R is the resistance, which actually rejects or oppose a portion of current uh, to flow through this circuit element. And we can determine this resistance by using the current voltage relationship applied to that element, and this relationship is nothing but the Ohm's law. So according to Ohm's law, we know V equals to IR. Okay. For example, this is our circuit, and where I current is applied, and for this current we have got a voltage V. That means in time domain, if we want to determine the voltage with the help of this provided current, we can determine the voltage easily using Ohm's law, which is Vt. Small v is actually the time representation of voltage, and small I is the time representation of the current I. Uh, so the current I in time domain, we can write it in IT, which is actually provided, and the provided amount is Im cos omega t plus phi. Here Im is the magnitude of the current, and this is the angular frequency, and this phi is actually the angle of the current. That means you can also call it the phase of the current. Okay, so if we convert this term, which is represented in time domain, if we convert this term into the phasor domain, we can get Im angle phi. Okay, if the function is cos, then we'll get this amount. You can I believe you know the conversion of time domain to frequency domain from the previous lecture, so I hope the previous lecture will help you to understand more about this conversion. Okay, I'm not going more detail about this conversion. If you have any confusion, just follow the previous lecture, the note of the previous lecture. So this is actually our current in time domain. To determine the voltage in time domain, we can use the Ohm's law to determine the voltage, which is small vt is equals to IR. I is here equals to IT, which is Im cos omega t. So again, if you convert the whole term into phasor form, then you will get RIm angle phi. Now, interestingly, you can see that for voltage, you have got RIm angle phi, where RIm is the amplitude of the voltage, and for current, you have got Im angle phi. The both current and voltage has the same angle, which is phi. Okay, so as long these two, current and voltage, has same angle, we can call it the phasor voltage and current of a resistor are in phase, because these two angle are same. That means they are in phase. The phase angle is same. Okay, therefore we call it the current voltage relationship of any resistor in frequency domain are in phase. If we convert this time domain circuit into the frequency domain circuit, we will have just these values. This representation will just change, and if we apply, if we draw this phasor relationship into the phasor diagram, and here we'll get for voltage V. For voltage V, magnitude is RIm. For example, this point is RIm, the real value, and the angle is phi. Therefore, we have got V. This is V, where this is the real part and this is the angle. Therefore, we have got this V. And for current, we have got Im. For example, Im is somewhere here. Therefore, we have short Im, and the angle is also phi. Therefore, we have got I here, and you can easily see this that the voltage and current are in line. That means they are in phase. This is the phasor relationship of a resistor. Okay. Take this note. Now we'll see in time domain how this look. We have already discussed this phasor diagram. In time domain, they will actually look like this. The black one is the voltage, and the blue one is the current, or in other way, if we provide this current to this resistor, then we will get this voltage. And interestingly, you can see this, the starting point of current and voltage and the ending point of current and voltage is same, because this is a resistive network and it has no phase difference. Therefore, we as long the phase difference or the frequency component is same, therefore we have got the same frequency for current and voltage in time domain. This is the response of a resistor. Now let's move on to inductor. What happened to the inductor? At first, the current voltage relationship of an inductor is actually Vt equals to L di by dt. This is the current voltage relationship in time domain. Okay. So if you are provided with the current I, which is IT equals to Im cos omega t plus phi, then if you differentiate this term, you will get minus omega Im sine omega t plus phi, and then convert this sine function into cos function. You can convert it by by introducing, that means the sine theta plus, we call it phi. The sine theta plus phi is equals to minus cos theta plus phi plus 90. So this is the conversion technique of sine to cos, and therefore as long there is an minus introduced, and we already have a minus here, therefore minus and minus becomes the positive, plus 1, minus into minus equals to plus, therefore this minus is gone. Here we have omega, we have L, we have Im, and the sign is converted to cos. Okay, so we have got omega L Im cos omega t plus phi plus 90. Now this is actually Vt, that means voltage in time domain. If we convert this time domain function into the frequency domain, we'll get omega L Im angle this term, which is phi plus 90. Okay, so now we'll further analyze this term. I mean you already know that angle phi plus 90, we can write it omega L Im e to the power, this part, if we elaborate this part, we can write it in this way: e to the power j phi into e to the power j 90. So e to the power j 90 is basically what? E to the power j 90, we can elaborate e to the power j 90 with cos 90 plus j sine 90. So cos 90 is 0, so we have j sine 90. Sine 90 is 1, therefore this e to the power j 90 will get j from e to the power j 90, and e to the power j phi is actually what? The angle phi. So it has become omega L Im angle, sorry, j omega L Im angle phi. So that means if we apply Im phi in an inductive network, then we'll get j omega L Im phi, or you can call it omega L Im angle phi plus 90. Let's deal with omega L Im angle phi plus 90. That means from this these two equations, this one and this one, we have got, we can see the clear phase difference. Here the phase is the provided current, here the phase is phi, and while the this current is applied to an inductor, we have got the voltage which is phi plus 90. That means in frequency domain, or the response of an inductor is like the phasor current of an inductor lags the voltage. See the current here, phi plus 0, this is the phi plus 0, and the voltage is phi plus 90 degree. That means this is phi plus 90 degree, you have to go another 90 degree, then you will get voltage. So this is how, as long the current voltage is the voltage angle is higher than the current angle, therefore we call it phasor current of an inductor lags. Current is lags as long as current is we actually in phasor diagram we move anti-clockwise, and here current comes first and voltage comes last, therefore we call it current is lags voltage by 90 degree. This is the typical and inductive response of a circuit element. So in phasor diagram, we have got voltage V equals to j omega L into Im angle phi. This is the voltage. Here you can see j omega L Im angle phi. So now if you want to find out the response, which is V by I, that means V divided by I, you will get j omega L. J omega L is the response of an inductor in AC circuit. Okay, so in resistive network, the response was R, which is the real value, but in inductive network, the response is what? The response is j omega L. How we have found out this response? We simply applied the Ohm's law, which is V by I. V by I is the response of the network, and V by I for an inductor is j omega L. That means this is the impedance of the inductor. Impedance is what? Impedance is the amount, impedance is the measure of opposing current, and we find the measure of opposing current by doing V over I operation, and this measure is actually called as impedance. So for inductor, the impedance is j omega L. Okay, and in phasor diagram, we can draw the voltage and current relationship. If current I am phi, then the current then the voltage is something omega L Im, which is a real value, into real value angle phi plus 90, which is phi plus 90. So you have to go these you have to go all the way phi plus 90 degree, then you can draw the draw the phasor of voltage. And here you can see the voltage leads current in inductor, or other way you can say the current is lagging the voltage for inductor by 90 degree. So this is the this is all about the inductor, and we can see that response in time domain. This is the current, applied current I, and here the response, here the voltage, and you can see this there is a 90 degree shift in current and voltage relationship, and we have found, we can easily see this shift into the frequency domain, or other way, if we measure this frequency and the shifting part, we will also get the 90 degree shifting. Okay, here you can see these two peaks are actually 90 degree shifted. This is the time domain response of an inductor. Now let's move on to capacitor. Capacitor, the current voltage relationship in time domain of capacitor is IT equals to C dV by dt. Okay, IT is equals to C dV by dt. If V is Vm cos omega t plus phi, the provided voltage is Vm cos omega t plus phi, then IT will appear as, by differentiating this term, minus omega c Vm sin omega t plus phi. Simple differentiation. Okay. Now this we have got sine. We need to convert this sine function into cos function by introducing minus cos omega t plus phi plus 90. So minus this minus and this minus will become the whole term as positive plus, then it has become omega c Vm cos omega t plus phi plus 90. Here also we have seen a 90 degree shift. Let's look at this deeply. if this is the equation of current in time domain, we can easily convert this equation into frequency domain, which is omega c Vm angle phi plus 90. Angle phi plus 90, we can elaborate this term into e to the power j phi into e to the power j90. E to the power j90 is what? E to the power j90 is j. Therefore, we have got j omega c Vm angle phi. Okay, so this is the current. This is the current of current through the capacitor in AC circuit, and here we also see that the current leads the voltage. This is the voltage. The current leads the voltage by 90 degree for a capacitive network. See, the phasor current of the capacitor leads the voltage by 90 degree. We can also okay, now let's look at what is the response. That means, what is the impedance? Impedance is simply what? V by I. Then V over I. If we want to find the V by I relationship of this equation, we'll get simply what? 1 by j omega c. Okay, 1 by j omega c is actually the 1 by V divided by I will be 1 by j omega c, and 1 by j omega c is actually the response of this capacitive network. That means voltage current relationship, voltage current ratio is 1 over j omega c, and therefore the impedance of capacitor in AC circuit is 1 over j omega c. Now let's introduce with another term, which is reactance. Reactance in AC circuit, we don't have any reactance for resistor, because resistor is a real part of impedance. Reactance and resistance, what is this? What are the relationship in impedance? The impedance, we represent the impedance with the letter Z. This is the representation of impedance. Z is actually nothing but the resistance plus J reactance. Let's see, I have introduced this term. Yeah, this is impedance. Impedance is nothing but resistance plus J into reactance. For resistive network, this term is 0. Therefore, we just have the R here. Just look at this. Where is this? Yeah. So this is R. We don't have any imaginary part of R here. Therefore, this is the real value, and therefore we call it resistance. Impedance is actually overall the reactive response and resistive response of a network. Okay, so we only have the reactance for inductor and capacitor. The reactance of inductor is nothing but nothing but omega L. J is constant. Omega L is the reactance. We express it by capital X subscript L, which is capital X subscript L. I mean, let me show you. X L is the reactance of inductor is equals to omega L. Okay, and XC is the reactance of what? Is the reactance of capacitor, which is 1 over omega C. So this is this is the reactance of capacitor and this is the reactance of inductor. So for inductor, this omega L is the reactance. You can also write write the voltage with JXLI, okay, where XL will be the reactance. Okay. So what we're talking about, the impedance, the reactive part and reactance part. For capacitor reactance is 1 over omega C. 1 over omega C is the reactance. That means 1 over omega C is the reactive part. Okay, so in capacitor, these are the current voltage relationship in time domain, and here this is the frequency domain. That means the phasor diagram of a capacitor. Here you can see the current and voltage relationship, and you can see here the current leads voltage by 90°. If we go to anti-clockwise, we will get the current is leading the voltage by 90° for capacitor. Okay, so this is the summarized version of resistor, resistor, inductor and capacitor, and this is the response. This is the impedance of resistor, which is R, and the impedance of inductor is j omega L, and the impedance of capacitor is 1 over j omega C. You can also write it minus j 1 over omega C, or minus j x C, or you can for capacitor, and for inductor you can write it JXL. That means JXL is the impedance of inductor, and minus J. Let me write it. Let's see, I can write it or not. That means, sorry, I don't have pen in my software. Okay, no problem. So just remember, just follow my lecture. For capacitor, we can write the impedance as minus jxc, where xc is 1 over omega c and minus j is actually 1 over j. Okay, so this is the summarized phasor relationship of different basic AC circuit elements, and here is also the detailed summary. Well, remember, in phasor representation, we actually write the voltage and current with the capital letter, and we use cap. That means V cap includes the real part, and the V cap includes the real part and the angle in phasor representation, and I cap includes the real part and angle as well. Okay, so here the time domain representation of these three circuit elements, and here the frequency domain, or in phasor representation of these three elements. Okay, we have already introduced with the term impedance, which is the response, voltage and current response of any circuit, and the reciprocal of impedance is Y, which is the admittance. Admittance is the allowance of current through a network. And here is the comparison of resistor, inductor and current relationship, and their impedance and admittance. Okay, now let's learn something interesting, which is the DC response and the high frequency response of AC circuit elements, especially the inductive response and capacitive response. The inductor will be treated as short circuit at DC. Why? At DC, what is the frequency? Omega. For resistor, there is a actually, if we talk about resistor, we don't have any any frequency term in the impedance Z. Here Z equals to R, which is a real term, and here we don't have any frequency. That means it doesn't depend on the frequency. But these two, that means inductor and capacitor, these are frequency dependent terms. You can see omega over here. Omega is 2 pi f. F is the frequency. Therefore, this L and C has a frequency response. As that means as frequency changes, the value, the impedance of inductor and capacitor will change definitely from their definition. Okay, so how this response is actually treated at DC? We know at DC frequency is 0. So when omega is 0 for inductor, the whole impedance will be 0. Zero impedance means what? Short circuit. Therefore, the inductor is treated as short circuit at DC. What about at high frequency? We can represent high frequency with the term infinity. That means if this term goes infinity, then ZL will also goes to infinity. That means if ZL is infinite, that means we can call it an open circuit because impedance is infinite. In open circuit, what we know, the resistance is infinite, and similarly we can also compare the impedance for inductor at high frequency as open circuit. Similarly, for similar type of analysis, if we apply it to capacitor, we will get at DC the capacitor will be treated as open circuit, and at high frequency this will be treated as short circuit. And you must, these two statement is very important, and you must know how to determine these statement and the validity of this statement, and you also need to know these two statements all the way of your engineering life. Okay, now let's move to how determine the impedance of a combined network. For example, this is a network where we have a resistor and an inductor in series. We need to determine what? Vt and It. Okay, no problem. Let's first determine the overall impedance, which is Z. Z is what? Z is overall impedance. That means as these two are in series, that means the impedance of this element plus the impedance of this element will be the Z, and therefore we can also determine the V and I. We can also determine the V and I. Vt is what? Vt is this voltage. We can easily find it. Okay, let's find out the impedance Z. Impedance Z equals to resistance plus the impedance of this element and the impedance of this element. Impedance of this resistor is 4, and the impedance of this element is what? This is inductor. Inductor is what? J omega C. Omega is what? Omega is 10 here. Therefore, J omega L. I'm sorry for this, for my mistake. L is 0.2. Therefore, J omega is 10 and 0.2. 10 into 0.2 is what? 2. Okay, so therefore the overall impedance of this network is 4 plus J2, and with this we can determine what? We can determine what we need to determine Vt and It. Okay, Vt is what? Vt It is what? We can determine the I cap first. I cap is what? V by Z. V is what? V is 5 angle 0. If we convert this term into phasor form, we will get 5 angle 0. 5 angle 0 divided by you can convert into this complex number into the phasor form, then you will get what? Actually they converted converted this term. They converted this term into the complex form. You can do whatever way you want, and you will get ultimately 1.118 angle minus 26.57. Okay, this is the value of current, and the voltage. You can apply the voltage divider rule, which is what, or you can, they have applied Ohm's law. You have current, you know the impedance, so you can determine the voltage. Voltage V equals to I Z. Z is what? J omega L. So they have evaluated voltage by using Ohm's law. You can also use the voltage divider rule. Whatever way you wish, you can determine the voltage. So this is the voltage and current as per this circuit diagram. Let's talk about admittance. Admittance is what? Admittance is the reciprocal of impedance, which is Y equals to 1 by Z. 1 by Z is what? 1 by Z is actually okay. 1 by Z is actually, if Z is R plus Jx, Y equals to 1 by Z. Y equals to 1 by R plus Jx. You can write R plus Jx into, you can multiply this R minus Jx term at the numerator and denominator as well. We are actually doing this just to eliminate J from the denominator. So a plus b into a minus b is a square minus a square. A plus b into a minus b is equals to a square minus b square, but here j square is equals to minus 1, therefore it has become r square plus x square. So you have got r square plus x square. You can express the whole term by r divided by r square plus x square minus j x divided by r square plus x square. So you have two terms. One is 1 second please. One is r divided by r square plus x square, which is the real term, and minus j divided by minus j into x divided by r square plus x square. You can also write it using the term r divided by r square plus x square plus j into minus x divided by r square plus x square. And this minus x divided by r square plus x square, we call it susceptance, and susceptance is the imaginary part of admittance, and the conductance is the real term of admittance. This is how we can also determine the conductance and susceptance of any AC network. Conductance is actually the how much real current is flowing through this network, and susceptance is how much the imaginary portion of the current is flowing through the network. This is susceptance. Okay, so this is the detail about the admittance. And the application of KVL and KCL in the network is very same as the application of KCL and KVL that we have learned in our circuit analysis. Here we also need to determine the overall impedance for the network. I mean all the theorems, which is KCL, KVL, voltage divider rule, current divider rule, all these theorems in AC circuit is as same as we have learned in the DC circuit, where only the difference is here we are dealing with the impedance, which is Z, and the representation of current and voltage are in phasor form. If these voltage and current is in phasor form and the impedance is represented in phasor form, we can easily apply KCL, KVL, voltage divider rule, current divider rule to the network. Here's a few examples. We also can determine determine the series and parallel network. We can find out the overall impedance of series network, overall impedance of parallel network, as the way we have learned in the DC circuit analysis. But here the additional competence that you need to solve the circuit is you need to know how to deal with the complex number, and the representation should be in the complex form. You can either use the complex number system, which is real part plus plus minus j imaginary part, or you can use the phasor form. In both way you can solve the network, and the impedance is as same as the resistor resistance in DC circuit, and other application of formulas like KVL laws like KVL, KCL, voltage divider rule, current divider rule are as same as we have learned in our DC circuit analysis. So here are a few examples you need to okay, let's try to learn how to solve this problem. This problem here, they're saying that determine the input impedance of the circuit where omega is 10. Okay, input impedance, that means overall impedance looking at this point. Here we have seen this capacitor and this resistor are in series, so we call it Z1, and this inductor and this resistor is in series, we call it Z3, and Z3 is in parallel with this capacitor. Now let's find out Z1. Z1 is nothing but this 20 plus 1 over j omega c. Omega is what? Omega is 10. 1 over j omega c is this one, and it has become the after evaluating we have got 20 minus j 50. This is z1 z1, and z3 is what? Z3 is 50 plus j omega l, 50 plus j omega l, and after evaluating this term we have got 50 plus j20. This is z3. Z2 is what? Z2 is this impedance of this capacitor. Impedance of this capacitor is nothing but 1 over j omega c. 1 over j omega c is what? Omega is 10, c is this, therefore we have got minus j25. So we have got z1, z2, z3. Z2 and z3 are in parallel, therefore actually they have done this overall, they have found the overall impedance, which is this Z1 is in series with this network, and this network is nothing but Z2 parallel Z3. That means Z1 plus Z2 parallel Z3. They have evaluated the whole thing using the series parallel network solving method, and after evaluation they have got this overall impedance for this network. So you can represent this impedance into this complex form or in phasor form. Whatever way you represent, either in complex form or in phasor form, or in that means in frequency domain, you can find the impedance in either way. Okay, So in this problem, they want to determine the V naught for this circuit. This is the V naught. This V is provided as input. We have these two elements in parallel. We need to determine the overall parallel impedance. Then we need to add this impedance with this network. Therefore we will get the total impedance. We have got the total impedance and we have got the supply voltage. We can determine the current through this network using the Ohm's law, which is V equals to IZ. We know Z, we know V, we need to know the I, that means V over Z. The overall impedance Z will be I, as when you have determined the current I, you can also determine the voltage V. They have actually used the voltage divider rule, but in my dictation I use the simple method. After determining the I, you can also determine V naught by multiplying I with this impedance. Okay, so this is simple. So these are few practice problems. You can practice it at home, and these solving methods will definitely help you in learning the AC circuit elements and their response. So that's all for today's lecture. Thank you so much for your patience and learning.